熊川です。ホエフリックです。
After it learns to leave the pointer, this is terrible. Sorry about that, guys. But I'm going to claim that this doesn't have problems if you write it correctly by walking through it. So if we're not doing a copy from, if we're just doing a regular copy from W to V, then I delete V's old value, I create some new value, copy over some stuff. Oh no, this is right. Yeah, we're copying from RHS footer. Okay. This is only wrong in that it uses the wrong kind of fleet. Phew. Alright. So we copy over the value and then we return this. Okay. Cool. That worked. We do not have a problem. Until someone tries to say V equals V. Assign from V to itself. What happens in that case? In that case, RHS is a reference, a constant reference to V itself. If RHS is a reference to V itself, and step one is we delete the stuff that V points to, and then we give it a new allocation, which has some garbage in it, like that might not even be integers, right? Which is garbage. And then we do this copy from RHS footer to our own, V's footer, but RHS would be the same object, so that's just a copy of the array to itself. So it still has garbage. I mean, the original data is gone at this point. We deleted it. So this would be a problem. Okay? Self-copy is a problem. But also, we have a problem in some cases if we have a templated or recursive data structure. Let's say that RHS is not a reference to V itself, but RHS is a reference to some heap allocated object managed by a shared footer, managed by a vector, managed by V. Okay, we have some complicated data structure. Notice that our naive vector itself is not a recursive data structure. It's not a binary tree or a graph or anything like that, but it can be used to create recursive data structures. In this case, our struct A might be something like a tree, right, with a vector of shared footers to its children. So now I say V is assigned the value of the vector of children of its first child. Right, I have a vector of nodes. I'm going to go to that first node, vector of children, and copy that into V. Okay, these are not the same object. If I had just wrapped my assignment operator in a simple, RHS is not this, then do this, otherwise do nothing, that's not going to help in this case. RHS would be different objects. But if the first thing I do is delete those shared footers, call their destructors, free what they point to, reads what they point to, and so on, RHS points into deallocated memory. As RHS.size, boom, it flips up. This is why I like copy and swap personally, because this takes what we do is step one in the assignment operator, we make a complete local copy of RHS before we do the very before we mess around with our old state at all. If there's any aliasing relationship, we fix the problem. So this is why I personally like copy and swap. You might say this only matters if you have a recursive data structure, and I think that's true, but we write a lot of templated data structures. So talk about another benefit of RAII, which again is this notion of putting your cleanup code into your destructor, right, and copy constructor, and writing those as a package deal. And that is that the slogan, RAII, resource acquisition initialization, the slogan's about initialization, but the meaning, when C++ programmers talk about RAII, right, you came here to hear a C++ programmer talk about RAII, and really notice that I'm talking about cleanup. The meaning is really about cleanup. It really should have been called resource freeing is deletion, right, or resource freeing is destruction, but that acronym was taken, so we had to make up our own. Destructors help us write code that is robust against exceptions. Right? C++ has exceptions. We've got try catch. We've got throw. When an exception is thrown, the runtime looks up the call stack. It finds the catch handler. It doesn't find when it calls terminate, but if it does, then it performs stack unwinding. Right? It brings that exception all the way up the stack, unwinding the stack as it goes. Those functions don't do what they were doing. They don't run to the end and return. Instead, the compiler destroys all their stack variables. Those frames are at this point dead, over, gone, and all of the variables declared in them are dead, over, and gone. Their lifetime is ended, and when the lifetime ends, we call it destructor. So that means to avoid leaks, all of your cleanup code should go in those destructors. Otherwise, if you try to do it manually, executable code in the body of the function, and the body of the function doesn't run, so here we have a pointer to an array of ints, and then since we called new, we know that we should call delete at the end of that scope, so we do that. But somewhere in the middle of the scope, maybe hidden inside a function call, something throws. And when it throws, stack unwinding skips us all the way down to the catch. We don't execute that line that I skipped over. And that means we don't free our resource. We don't clean up. This is not good RAI code, because it leaks memory. Not just not good code, this is bad code. It's buggy. So what we're going to do is we're going to make a little of our own. It's just going to be a little struct. It's going to hold our pointer to an int in it. We're going to have a constructor that can give it a pointer, and in the destruct, we're going to delete that pointer. And that's all we're going to do. By putting that responsibility for cleanup into the destructor, we have actually fixed our code. We fixed the leak. Now, when we throw that runtime error and it skips down to the catch, well, number one, notice it's not actually skipping the code. We didn't have anything to do after that throw in this little example, other than clean up, and we certainly don't want to skip the cleanup. Anything we don't want to skip, we're going to put in a destructor. So that destructor is going to run when that variable ARR is cleaned up. and it's going to get cleaned up during stack unwinding, get cleaned up when we hit that closing curly brace. Any way we hit that brace, it goes away. We call it destructor, we delete the pointer, we clean up. That's what we wanted to do. Now, this is still relatively dangerous code. I wouldn't want to say go home and write a pointer that looks exactly like this.
今の
This is what we
歓
need
迎
to do is delete bracket O, then hit star. But we would like it to be more generic. And we also like it to be a little bit safer, because notice, destructor, I did not give it a copy constructor or a copy assignment operator. I didn't follow the rule of 3. And that means that RAI pointer is copyable. If someone made one of these and then copied it to another one, then both RAI pointers would think they were managing the same allocated memory. I would get a double delete, right? Just like in the naive vector example. Fix that. Do I want RAI pointer to be copyable? I actually don't want it to be copyable. And so I can improve it by making it non-copyable. The way I do that is I delete its copy constructor and its copy assignment operator. So my function definition has, instead of curly braces for its body, if it just has equals delete, then we call that a deleted special number function, or deleted function in general. And the compiler will reject calls to that function at compile time. It will say, I see you were trying to call this function, but this function has been deleted. You are not allowed to call it. This prevents our users from trying to copy these things. Notice also this facility that's equals delete, even though I am using it in a class whose destructor is deleting a pointer. That use of delete and this use of delete have nothing in common. Right? They're completely unrelated. They're just spelled the same. New keywords are expensive, so they reuse that one. They also reuse default. Speaking of default, what else can we do with a member function besides delete it? Well, we can explicitly default it. If instead of saying curly brace body or equals delete, I say equals default, then the compiler will create a defaulted version of that function just as if it had been implicitly generated. Right? And it will do it even if it would not have implicitly generated that function to begin with. So explicitly defaulting your special members can help your code be self-documenting. It can say, yes, I considered the fact that I might need a copy constructor, or I might need an assignment operator, or I might need a destructor, and I have decided that the default ones work fine. It helps your code be self-documenting to explicitly default your special members. It occurs to me I should take questions if there are any. If you have a question and you want to go to the mic, that would be cool. Okay, cool. So the ability to default special members leads us to 0. If your class does not directly manage any resource, but instead uses library components such as std_vector and std_string, then you should strive to write no special member functions at all. Default them all. Right? Maybe write them out and explicitly equals default them. Let the compiler generate your default destructor. Let the compiler generate your copy constructor and your copy assignment operator. Maybe write your own swap. There's no way to default the swap at the moment. There is the standard swap template that does the move and then move and then move. If you think you can do better by just...
So if you're allowing rule of 0 and the compiler is going to generate all your special member functions, you just said to write your swap, which implies that the compiler knows to call that swap which you wrote.
If you write a member swap function, then no, the compiler doesn't consider that magic. Except with ranges, maybe, I'm not sure. If you write your own friend overload swap with 2 arguments, then standard library algorithms will call that swap. They'll use argument-dependent lookup to find it. It is, in some sense, associated with your class in the same way that your operator equal and non-equal and so on are associated. We'll see examples of writing a non-member swap in the slides, although I don't explicitly talk about swapping. Alright, so this is known as the rule of 0 by analogy with the rule of 3. The rule of 3 says if I need to write a destructor, I probably also need to write copy constructor, copy assignment. They come in 3s. The rule of 0 says write 0 of those. You know, you can't always get this, but most of the time we would like to write 0 of these things. Let the compiler default them all. So prefer rule of 0 when possible. I would say there are 2 kinds of well-designed value semantic C++ classes. The first kind, and the kind you should strive to write, are business logic classes, domain classes, in the domain of whatever you're doing. They don't care about resource management. That is not the job that your code is doing. Your code is solving a problem. It's not managing resources. It should delegate that job of managing resources to data members of the class. And those data members should be of types such as std_string, std_unique footer, std_shared footer, std_vector. Maybe not even unique footer and shared footer, but if you're going to be allocated resources, then yes, you would use unique footer and shared footer. Right? Use these data structures that are RAII, that follow RAI by default. Right? It's only if you need to write a custom resource management class, a small single-purpose resource management class that manually manages a resource, right? A file handle class, a unique footer class that manages a memory allocation, a unique lock class that manages vtext lock. Right? These are the kinds of things that would need to follow the rule of 3 because they need to do some cleanup in their destructor. And in those cases, the resource management classes, they would acquire the resource destructor, free the resource in the destructor, copy and swap in their assignment operator, and they would also have a copy constructor, move constructor, things like that. Or they would explicitly delete them if they want to be non-copyable. Speaking of move construction, introducing R-value references. Now, I was a couple of hours on this yesterday, so hopefully this is review for those of you who are following the track. But for the rest of you, we're showing up here, C++ 11 introduced R-value reference types. The references we've seen so far with a single ampersand are L-value references. L-value and R-value come from the syntax of assignment expressions. An L-value can appear on the left-hand side of an assignment. Examples of L-values are X, star P, A sub 2. These are all L-values, generally speaking. So many of those are hints, then yes. R values are things that appear on the right-hand side. So they're things like 42, minus x plus 1. Those cannot appear on the left-hand side. Right? Those assignments on the right-hand side, those will not compile, because you can't assign to an R value. R value must appear on the right-hand side. Int rep, we call that L value reference to an int. Int rep with 2 ampersands, we call that R value reference to an int. As a general rule, L value reference parameters do not bind to R values and vice versa. There's one special case around compatibility. If I pass an R value such as 42 to a function that takes a constant int rep, that will bind even though 42 is an R value. If it's const qualified, then I can bind an L value reference to it, generally speaking. So here, for example, I have a function f that takes an L value reference. I cannot call f of 42. 42 is an R value. It doesn't have an L value reference. I have g only accepts R values. I cannot pass a name y as an L value. It actually rejects L values. It only accepts R values, such as 42. H for backward compatibility accepts